Hello everyone, this is Pawan Mirla. Today's guest is Professor Doyne Farmer, a world-renowned physicist and complexity economist. Welcome, Professor.
Nice to be here.
Professor Doyne's career spans using chaos theory to beat Las Vegas roulette to revolutionizing how we understand global markets. As a professor at Oxford University, he is currently pioneering new ways to model the world's most complex systems. We are thrilled to have him here today to discuss his incredible journey.
Happy to be here.
So, Professor, thank you very much for joining us. May I begin with asking you about modeling complex systems? In your book and elsewhere, you have discussed how you have recommended a new approach to model these complex systems. Could you tell us about these systems and how you model them?
Well, in a way, it's very straightforward. Complex systems are systems that have emergent properties. That means that the components of the system may look very different than the system as a whole. A neuron is a cell. You give it a signal, electrochemical signal, and another signal comes out of it. It's like a little transistor or something. But you hook 80 billion of them together in the way they're hooked together in the human brain, and you get something that you never could have guessed would happen just from looking at the neuron itself, unless you already knew that such things were possible. So that's what complex systems are about. Now, what we've learned is that because they're typically highly nonlinear, they're hard to understand just with pencil and paper. You typically need to at least begin by simulating the way the components, how they interact, and then demonstrating that you can see their emergent behavior in the computer. And once you do that, then you can start dissecting it to see what's going on. What is it that really causes it? What happens if you change it this way or that way? So that's the kind of modeling I do and others do as well. I think the new thing is applying that to economics. Again, others have done that too, but we're getting models that are getting closer and closer to competing strongly or overtaking conventional economic models. In fact, in some cases, I can say we've already overtaken conventional economic models.
So, would this overlap with agent-based modeling?
Yeah, the distinction is if we were modeling a physical system, say stars who might or might not form galaxies, there's no agency. The stars just follow Newton's law. But if we model a social system, then we have individuals who make decisions. That's even true already sometimes if we're modeling animals, but it's particularly true if we're modeling people who have agency. They could decide to do this or they could decide to do that. And so that word is just emphasizing that we have to do that, and that's the hard part of the modeling exercise, is understanding how the individual people will behave.
Mhm. Since humans make decisions and there is the behavioral aspect, I assume with traditional models, it's hard to incorporate that behavior aspect. So with agents, as I understand, it can be modeled. Can you give one example of how it applies to, say, in context with economics, and maybe one example with, say, weather predictions? An agent's behavior affecting others' behavior, and collectively it affects maybe the system. So I'm trying to understand how this is modeled. Now, how does someone model this? Say, if, the listeners would be wondering, how do I get started, and how much domain knowledge do I need for this?
Yeah. Well, so first of all, economics is precisely about what you were saying. That is, we all do our individual behaviors, but we collectively affect each other. The first instance is just we're all in the modern world very specialized. Yet we depend on all the goods and services all the people with all the other specialties provide to us. We provide them with our good or service, and the other, 7,999,000,000, etc., provide us with their goods and services. So, and when we have something like a recession, It's because collectively something happened that none of us controlled, but it happens as a result. It's an emergent behavior of that interaction. Now, by simulating from the bottom up, we can really see that. We can go all the way from microeconomics to macroeconomics. We can go all the way from microeconomics to macroeconomics. And in fact, the macroeconomics emerges from the microeconomics. The challenge is to get the behavior of the individuals in the simulation to be realistic and even predictive of what might happen in the future.
In this aspect, now how do we distinguish chaos from randomness? So as we model with these agents, and we have given preferences of that particular for that agent, and also maybe the average across all the agents, there is some aspect of randomness. So where is the chaos here?
Yeah. So let me maybe first explain why that would be interesting. It's because economies seem to often generate endogenous motion. What does that mean? It means that things change in the economy and the changes come from inside the economy, not outside the economy. So the opposite is, say, COVID. We had a virus that's outside the economy, at least initially. Then it starts making people sick, and then that causes people to take economic actions that cause an economic depression, a recession.
Mhm.
And so, but if you take, say, the 2008 crisis, that's an example of a crisis that came from inside the economy, because how did it happen? We came up with the idea of mortgage-backed securities. Banks began selling a lot of them. Everybody owned them all over the world. They depended on the housing market going up. But we also loosened lending policy as a result of mortgage-backed securities so that more and more low-income buyers could enter.
Mhm.
And at some point, we started to run out of low-income buyers. The low-income buyers were much riskier anyway. And so that caused the housing market to start going back down.
Yeah.
And that caused the mortgage-backed securities to lose their value. And because everybody had them all around the world, that caused banks who
Mhm.
held large numbers of them to stop lending. Stopping lending then slows the whole economy down, and we had a recession. So
Mhm.
you see this complex chain of events, all are happening inside the economy.
Mhm.
And in order to understand them, we have to model those events.
Mhm.
And we can do that with agent-based modeling. The mainstream approaches, to be honest, can't really do that. For several reasons, they can't model in enough detail
Mhm.
they won't have mortgage-backed securities inside them. They
Mhm.
might have overall lending, but at the time the crisis happened, they didn't even have the possibility that the people that were being lent to, that the borrowers could default.
Mhm.
So they couldn't even really, they weren't even, as somebody said, they weren't even good enough to be wrong. Um, uh, okay, but now you asked about chaos. How does that fit into the story I just told?
Mhm.
Well, how do you get an economy to move endogenously? So now here I need to put on my dynamical systems hat,
Mhm.
back to my days as a graduate student. And in a dynamical systems, one of the remarkable things you learn is there's only a certain number of possible attractors a system can have. Attractor means, okay, you knock it in some funny state, like a mass on a spring,
Mhm.
you pull the mass up, you let the spring oscillate, friction will slowly bring it back to rest. So that's the attractor. That's a fixed point attractor. If you take a metronome, the metronome's going like this, you knock it, you might change its phase, but it goes back to going back and forth like this. That's a
Mhm.
limit cycle.
Mhm.
Now you can have a complicated version where you have effectively like two metronomes with different frequencies that don't resonate with each other, and then you get a torus attractor, but that's a detail here because
Mhm.
that's as bad as it can get. After that, the attractors become chaotic, meaning that movement on them, if you don't know what's happening, it might look random,
Mhm.
and uh, and uh, and and you have endogenous motion. So as with the limit cycle, you have endogenous motion, meaning the motion kind of comes from nowhere. You wouldn't be obvious that it would even move from looking at
Mhm.
the equations.
Mhm.
It's like if you're standing by a mountain stream and looking at the stream and you notice the water's constantly moving, you see eddies, and you might even get splashed as you're just standing there by the water.
Mhm.
Now, what's causing that splash? It's not because the rocks are moving. It's not because some kid is back there with a squirt gun.
Mhm.
It's because the motion of the water is chaotic,
Mhm.
which means it both moves spontaneously on its own and it moves in an unpredictable manner. And so that's what chaos is.
Mhm.
Now let's go back to the economy. How is the economy making these changes all by itself that make it hard for us to anticipate them? It's because, I argue, it's because it's chaotic. That's a hypothesis, but we see that in simple models. And 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 so and in this case, we know it's not a limit cycle because the economy is not just rocking back and forth.
Mhm.
We know the motion is generated internally from the story I just told.
Mhm.
So what else can it be? Because back to dynamical systems, there's just only those possibilities.
Mhm.
And so that's why I hypothesize that the economy is chaotic. And it's important to understand because it actually helps us predict what might happen. Now, that might sound weird because I just said chaos becomes unpredictable. But in
Mhm.
chaos, what happens is that two states that are almost the same, two configurations of the stream that are almost the same, but they differ in a small part.
Mhm.
Over time, those differences become exponentially bigger. And meaning that if you go far into the future, things will look random because tiny differences are being amplified and you can't make measurements that are accurate enough to distinguish the two
Mhm.
states of the world. But but in the economy, similarly, we can have sensitive dependence to initial conditions, but over the short term,
Mhm.
we may be able to predict things. If we understand the structure that's underlying what seems to be random,
Mhm.
then we can make a model that can take advantage of that to make short-term predictions.
Mhm.
And secondly, we can make statistical predictions. Like I might not be able to predict exactly what's going to happen, but I can predict on average it's going to be something like this. We're familiar with this from the weather.
Mhm.
You can't predict the weather more than 2 weeks out, but you can predict the climate years ahead. That is,
Mhm.
I know in January it's much more likely to snow than it is in June, and that
Mhm.
exists even though the weather system's chaotic.
Mhm.
So we can still make statistical predictions, and we can still think about making policy changes and asking, on average, what will be the result of those policy changes.
I see, Professor. And when we model an agent behavior, say a behavior of a consumer or behavior of a firm, how do we connect them? How do we build a network on the causal effects? Because firms come in various sizes and they differ country to country. The legislations maybe are different. Say, for example, uh, the agents being simulated in India versus agents in Europe versus agents in US. Uh, uh, Maybe they are connected in some way, but how do you find those connections? And how do we have the dimension of time? Because within these systems, time makes a big difference. Maybe change in regime, maybe change in something else, demographic changes. So over time, the agents behave differently. So it's sort of a time series of agents' behavior. So network plus time series adds more complexity to this.
Yeah. So that's precisely what we do in an agent-based model. The agent-based model is itself a dynamical system
Mhm.
and has an initial state. We set it up at the beginning. We tell all the agents in the system, you have this much money, you have this much information, this is your role. And so the agent might say be an individual who lives in a household, who works for a firm, who consumes goods.
Mhm.
Um, they might lose their job. They might get a new job. They might even start a new company.
Mhm.
Um, so, so we simulate those roles of agents.
Mhm.
Now, the key in any prediction of the world is finding the things that don't change, that you can use to say how things will change in the future. You always have to have something that doesn't change. So in this case, we assume we have a rule for the way the agent's going to make decisions
Hmm.
that won't change. The decisions might change, but the rule doesn't change. Now, the rule might even involve learning, might even involve the agent thinking, but that's still part of the rule, the model that we have for that agent.
Hmm.
Okay. So then what we do is we start the system, we initialize the system. The agents all take in information about the state of the economy.
Hmm.
They all make a decision about how to react. So, one might quit his job, the other one might start a new company, etc.
Hmm.
Then, then we see what the economic consequences are. Uh, the agent loses his job. He doesn't have a salary, so he's not going to buy things anymore. So we
Hmm.
see the effects start cascading around the economy from each individual. Then, so that creates new information because the economy changes state. GDP might go down a little bit.
Hmm.
And then we take in new information. Maybe there's a COVID pandemic, or maybe something happens from outside the outside world.
Hmm.
And then the agents make decisions again, and they have economic consequences, and we just go around and around that loop as many times as we like.
Hmm.
And the time scale could be days, months, years, depending
Hmm.
on the kind of model we're building.
I see. And how do we separate local versus global? Because each county may be different, each state may be different. So
Yeah.
do we have different models for different levels? Just like as in weather, I remember in one of the blogs you mentioned the weather is not done at the global level. It does regional level. It matters. It might rain in one place and close by it may be dry. How does
Yeah.
it apply for this?
So let me first clarify that remark in that the global weather does matter. The weather here is connected to the weather in England is connected to the weather in France, right? But uh, it varies a lot. It may be that it's sunny and warm now, as it is at the moment here, and it may be that it's raining in Africa quite hard.
Mhm,
They can even have a typhoon or something in Japan. So
mhm,
the weather differs in different parts of the world.
mhm,
Now, but to really understand the weather, you need to be simulating the weather in all the different parts of the world and the way the weather's interacting. And when you do that, you do see this turbulence as it moves around the globe.
mhm,
Now, similarly for the economy, we need to be simulating all the different pieces of the economy, at
mhm,
least ultimately, to do the best job. And we need to understand how they're interacting
mhm,
and how the collective behavior of the agents in the model
mhm,
changes the macro behavior, which also involves the agents responding individually to the macro behavior.
mhm,
If there's a depression, people are going to be looking for work.
mhm,
So, and they're going to be consuming differently. They're
mhm,
going to be changing their behavior in many ways. So it's very closely analogous to the weather. Now, the standard models, it's as if you tried to just assume that you could model the weather by just knowing the global temperature and pressure and humidity.
mhm,
Uh, it maybe makes a little more sense for the economy than it does for the weather,
mhm,
but you're missing a whole lot when you do it that way. Now, mainstream economists are trying to put in heterogeneity so that they can have different parts of the economy being different from each other, like old people behaving differently than young people. They certainly do that.
mhm,
But rich people behaving differently than poor people, or even people in India behaving differently than people in the US.
mhm,
They have a hard time doing that at any level of detail.
mhm,
Whereas in our agent-based models, we just give them different characteristics.
mhm,
If you're a German, we say, well, Germans all like to save. So the Germans are going to save more than the Americans who, will be running up their credit cards while the Germans are putting money in the bank
mhm,
under the same circumstance.
mhm,
And that's important to understand. Again,
mhm,
much harder to do in a standard model.
mhm. I see, I see. And Professor, the rule in an agent, is it the expected behavior? Now, how do we define a rule?
Well, a rule could be, for example, um, imitate the best. So we have a model where the agents from time to time look around the world
Mhm.
and they go, and they're trying to decide how much to save, what fraction of their income to save. They look at their neighbors and they say, which of my neighbors is doing the best? And then they knock on the door and they say, how much are you saving every year? And they take the answer and they go, okay, I'm going to do the same because I can see that guy's doing really well.
Mhm.
So it's a very simple algorithm. One of the things we're able to show is, depending on how you do it, but you can actually get an answer that's very close to what a completely rational agent would do, who's saying, I want to maximize my consumption and I'm thinking about discounting into the future and so on. Those really stupid imitating agents were just imitating each other. None of them is the leader who's thinking,
Mhm.
can actually find the right answer for saving and get pretty darn close to the rational agent.
Mhm.
Now, that said, in our model, depending on how often they're waking up or how often they're looking around, they can also start to oscillate.
Mhm.
So some of the agents are saving a lot, some of them are not saving so much,
Mhm.
and the population swings back and forth over time. So you automatically get booms and busts,
Mhm.
and you get a division of the world into the rich and the poor,
Mhm.
because the rich who are saving a lot get richer, and the poor the opposite. So just an example, a very simple rule
Mhm.
that actually can be very powerful. I mean, in other cases, the rules are dictated by institutions. I have a model where, um, assume we're modeling investment banks, and what do? They follow what they're told to do under Basel II,
Mhm.
which is, the investment banks are borrowing money to buy more assets than the other ways could, using what's
Mhm.
called leverage.
Mhm.
So, which played a major role in the financial crisis. The
Mhm.
fact that everybody was too leveraged was ultimately the cause of the crisis.
Yeah.
And so, but under Basel II says, if your prediction for volatility is that volatility is low, you can borrow a lot of money. If you predict volatility is high, you've got to pay some of your loan back and borrow less,
Mhm.
take a smaller position.
Mhm.
So, in fact, people were doing that. They were predicting volatility by using a moving average of past volatility.
Mhm.
And then you can show that without a couple of other very simple assumptions, just that simple behavior can cause chaotic behavior in the financial system. That is, you
Mhm.
can have a 10-year-long gradual boom
Mhm.
followed by a very sharp crash in the market,
Mhm.
much like what actually happened.
Mhm.
And it's very hard to anticipate because, and let me just say one other thing. If only one agent is doing that and the other agents are just, the other banks are holding their portfolios constant, no problem.
Mhm.
That agent that's doing that is going to do well and do better than the others.
Mhm.
But if everybody's doing that, then you have a systemic risk.
Mhm.
And what it means is that when the asset that they're all invested in drops in price a little bit, then the agents who are fully leveraged have to sell some of the asset to pay their creditor back.
Mhm.
They're
Mhm.
all selling at the same time. So that pushes the price down more, which causes more selling, which pushes the price down more. And that's what causes the crash.
Mhm.
So you can see what's causing all this in the middle of it.
Mhm. After we have the agent behavior simulated and the outcome analyzed, estimated, how do we communicate it? How frequently do we communicate with the stakeholder? Say our sponsor is a regulatory institute. So I have built these models. I'm seeing a new order, new regime, new behavior. How frequently do we communicate with the stakeholder? Let's assume we have a regulator as our client. So how do we communicate with them? How frequently do we communicate? And what should be their level of understanding?
Well, it would be up to the stakeholder to decide how often we would communicate and whether we just communicate regularly or whether I'm supposed to report with my model. I spot something dangerous. I call up the regulator.
Mhm.
These kind of things are sort of personal relationships and common sense, I would
Mhm.
say. Um, but you are getting at the idea that of what we would want to do. We would want to be able to look for danger points and be able to take action to make those dangers less bad,
Hmm.
or maybe even avoid them entirely.
Hmm.
And that might sound funny because I'm saying we're trying to predict the future, yet we're trying to change the future. But that's the main reason we make predictions about the future, is to change it. We make conditional predictions that say if the things keep going this way, this is where we're going. I
Hmm.
don't like that, so I'm going to change my behavior and go in a different direction.
Hmm.
That's why we make predictions.
Yes. Professor, some readers of the book Managing Chaos might understand it incorrectly, assuming that the traditional models are useless. We got to use the agent based models. As I understood, you're not telling people not to use the traditional models, but they apply in a different context. Based on complexity, you need different type of models. So could you tell a little bit about that, your thoughts, and if my understanding is right?
Yes, no, you understand me perfectly well. I think there are situations where mainstream economic models are very useful, and I'm not saying we should stop using them. But there are other situations where I think they're not so useful,
Mhm.
and there are some situations where agent-based models could be particularly useful.
Mhm.
My call in making sense of chaos is to give more resources and attention to agent-based modeling, allow young economists to start careers doing that, and and provide the funding that's needed
Mhm.
to the bring the method to fruition so that it can really achieve its potential.
Mhm. Professor, with respect to the way we model feedback in an agent based system, the new emergence of reinforcement learning with deep learning methods has immense power, where we monitor the state, the action, the reward, and a cumulative reward over time, and we model the feedback. And with LLMs, we are able to model very complex states and complex outcomes, multidimensional outcomes. So, what is your take on this? Now, the use of reinforcement learning in EVM?
Yes. Well, so first of all, it's a hot topic of research right now to see what role they can play and how well we can use them. Reinforcement learning so far has the limit has been that it takes a lot of computing power.
Mhm.
You know, when uh, Google DeepMind did AlphaGo, the rules of Go are simple. The decisions the deep learning algorithm is making, or the reinforcement learning algorithm is making,
Mhm.
is limited. You just put a piece on a board. Economic models are more complicated, at least if you want to make them realistic.
Mhm.
Uh, LLMs also, people are looking with a lot of attention at, can we use LLMs as agents? We basically tell the LLM, behave the way a person would here.
Mhm.
Make the same decisions a person, and you have to tell the agent, the LLM, you're this kind of person. You know, you're 55 years old, you're a woman, work as a manager of a factory. And so so there's a lot of attention to that. The jury is out at how well it will work. Um, There are some tasks where we know that these techniques don't work very well. One is time series prediction. So if
Mhm.
I give you a series of numbers, say from uh, sunspots,
Mhm.
and you want to predict how many sunspots we'll have next year, simple nonlinear methods that
Mhm.
my colleagues and I developed a long time ago work better. Actually, we're working on a paper that demonstrates that in those kind of problems, uh, these simple methods actually beat these fancy foundation models or uh, reinforcement learning models or deep learning models or quite quite handily. Uh, but so they have great promise, but they also have limitations.
Dishes. Yes, Professor. Okay. Uh, and Professor, in regards to your experience with predictions company, uh, could you tell us how you use dynamical systems in those days, and what you think could have been different considering now you have AI?
Yeah.
Do you have used AI? How would have AI used or the lessons learned from predictions company?
Yeah. Well, so Prediction Company happened it began in 1991, and I left it in 1999. It went on beyond that. But, uh, but we did, we bought data from data providers,
Mhm,
first of all, and then we analyzed that data looking for pockets of predictability. That is, stocks are very noisy, but once in a while you find a signal that tells you this stock is likely to go up or that stock is likely to go down, and you can make a bet on it.
mhm,
Um, we did use methods that we developed for predicting other things to do this. Um, we were motivated by the fact that at the time, the prevailing wisdom was that markets were efficient, meaning that they were intrinsically unpredictable and it was impossible to make money by anticipating what a stock was going to do unless you had insider knowledge about that stock. And so I think we were able to show that was wrong quite dramatically. Others also did the same. But yeah, overall, it was a matter of finding patterns and exploiting those patterns in the data. Excuse me, I realized I didn't answer the other part of your question. With AI, if we had AI now, um, well, we could do a lot of things much better. First of all, one of the things we've learned since the 90s is when you're using neural nets, and we were using neural nets in the 90s,
mhm,
but it works much better to have many hidden layers in the neural nets.
mhm,
And so had we known that, we would have pushed in that direction, though the computer time was much more limited in those days. That's a huge
mhm,
difference from now.
mhm,
Um, if, if, and if we'd had LLMs, we would have had the LLMs reading the newspaper and creating signals that would have gone far beyond the ones that we were getting from the data feeds that we were running. And we could have used the LLMs to make sense out of patterns that we otherwise would not have been able to see.
I'm curious, when you used neural networks in 1990s, it was very early times, and compared to this era of AI, we are able to use embeddings for categorical variables, embeddings for company descriptions. We have embeddings provided by institutions, or we could develop our own embeddings that give a lot of context. So instead of using one hot encoding, so you have an embedding that has context baked in. Uh, so companies like Google and Microsoft may show up similarly in the embedding itself, and embedding becomes a feature set that gives much richer feature set that could be used for very relevant outcomes. How did you handle? Was it a limitation in those days, or was there any alternative for that?
Well, it was a big limitation. We would certainly have been using embeddings. We dreamed about something like that. But to be honest, I think one of the main uh, things that enabled our success was effectively manually building a good embedding. We created signal filters for prices. So we didn't just take the raw prices and directly build a model. We took the prices coming in and we applied signal filters, low pass filters, high pass filters, uh, comparisons, um, wavelets, all the whole fancy technology that signal processors have developed. And then we spent a lot of time by hand figuring out which of those features were useful. And we developed a lore so that we knew what was likely to work when we put it in a model for a new thing. So we did a very crude version by hand that took us years
Hmm.
of something that, a modern, uh, uh, you know, transformer can do in, a day.
Yeah. Yes. I wanted to hear your thoughts on collective awareness and reflexivity concept. I assume it's that feedback loop happening, one agent behavior affecting the other agents, and collectively outcomes change. Could you tell us more about collective awareness and concept of reflexivity? How is it different from the regular feedback loop?
Yeah. So by collective awareness, I would mean that you're aware of some things. I'm aware of some different things. Now, if we're not interacting, neither of us benefits from that. But if I tell you, you know what, I just noticed, Pavan, this
Mhm.
happening, you tell to me what you're seeing, then now we're both more aware than we were before.
Mm.
So that's happening at the level of the whole planet. And I would, my vision is that we go beyond just collective awareness to have become a conscious civilization. That is to build models of our collective selves so that instead of just letting everything that happens in the world just happen as we do now, right? Uh, Politics and uh, geopolitical events just unfold.
Mhm.
Um, but but if we understood the cause and effect relationships better,
Mhm.
we could anticipate how our collective action would change things and maybe steer the world in a better direction than we do now.
Mhm.
It's a big dream, I recognize, and I don't think politicians are. I'm not imagining politicians are really scientists who always act on the objective truth.
Mhm.
But on the other hand, if the models get good enough, and if they're either actually trying to get the best things for their people, or if they want to have a good outcome so that people will continue to like them,
Mhm.
then we could start doing this. And I think this, with agent-based modeling, this is becoming within range. It's
Mhm.
conceivable that society can do it.
Mhm.
Now, reflexivity is a bit of a simpler thing. I think reflexivity is just, you know, I do something to you, then that causes you to do something to me, and around the loop. And so we really need to be thinking about the feedback loops when we're modeling the world and when we're reasoning through what will happen in the world
Mhm.
and new situations.
There you mentioned about the levels of modeling. You have mentioned three levels of modeling. Could you tell a little bit about that? How do you distinguish the modeling levels, and how is
Yeah.
it related to the collective awareness?
Well, so at one level, and this is the first thing we got good at modeling, we can model other things out in the world. So we model our environment. Newton realized that by making a very simple assumption about what causes an apple to fall,
Mhm.
he could actually explain the way planets moved in the sky. And that's quite remarkable. Uh, it means we can predict eclipses, we can put rocket ships in space and successfully predict where they will go and get them back. Um, Now, the next level of awareness would be thinking about how those things are affecting us. So, to take that example, if if there's an asteroid approaching the Earth, being able to detect the asteroid and deflect the asteroid would be hugely valuable to humanity. We model the weather. So we're modeling that. Well, that's still modeling our physical environment, but we also have cat modelers who work for insurance companies who are modeling the impact that a hurricane will have on Florida.
Mhm.
So again, modeling the effect of the physical world on us directly.
Mhm.
But the hard problem, I mean, because who, what is it that causes most of the bad things that happen in the world? I don't think it's the environment. I think it's us.
Mhm.
We create our own problems.
Yeah.
And so if we can anticipate those problems by saying, oh, wait a minute, if you guys keep doing this, this bad thing will happen.
Mhm.
You know, to take a concrete example, let's go back to the aftermath of the 2008 crisis. They bailed out the banks. Now, they could have bailed out the households. This is a much debated question.
Mhm.
And we will never know exactly what would have happened had the households been bailed out. But
Mhm.
my hypothesis is that had we bailed out the households, we might not have Donald Trump as the president of the United States right now. Why? Because, the common man got angry. You
Mhm.
Democrats say you're for us little guys, but when push came to shove, you bailed out the bankers, the rich guys.
Mhm.
You didn't protect us poor guys.
Mhm.
So, so, so again, these things have longer term consequences. And I
Mhm.
think if Obama had had a model that could have showed him the state of the world
Mhm.
under the two decisions he had to make,
Mhm.
he might have made a different decision.
I wanted to ask you about your methods of learning things because you have multidisciplinary interests as a physicist and a modeler and making predictions, you need to understand a lot of concepts and connect them together. So, for the listener, I was wondering if you could share how you learn, how you keep learning, and what's your method of maybe in taking notes or something? Maybe it could be personal, but any insight that could affect the next generation, which is very uh, keen on looking for quick learning. With ChatGPT, we go and ask for an answer. We are not thinking; we are bypassing the thinking process. So, what would be your advice for the younger generation?
Well, uh, when I was a kid, I was very bored because I didn't have social media, internet, none of that existed, of course. So I did a lot of reading. So I learned a lot about the world, and I spent a lot of time just thinking, which I think is hugely useful. Um, and I still today, to be honest, I almost never listen to podcasts. I don't, you know, I spend my time thinking when I'm have downtime. Uh, Curiosity, being curious it means you automatically learn. And as a child, I was probably exceptionally curious. My observation is that that's kind of wired into people. Some people are just wired to be curious, but it's a good thing to develop. Don't let it die in yourself, and find the things that you really find fascinating and learn about them, because if it's fascinating to you, you'll just learn it automatically. You don't have to work at it. Um, uh, Another is it's much faster to learn by asking questions. If you really want to learn something, you know, skip over the stuff you more or less understand and get to the thing you don't understand and then ask a question. And so, if I want to learn about biology, the best way is to go find a biologist and just start asking them questions and having a conversation. And then I can quickly get to the thing I wanted to understand.
Mhm,
Um, and I'm an odd person in that I'm really a generalist. I know a little about a lot of things, but I know that it's important to work with people who really are specialists, who really understand things deeply.
mhm,
And you shouldn't fool yourself into thinking you understand something that you don't understand. And you
mhm,
should really work together with people who understand the specifics, the domain knowledge of
mhm,
the system that you want to understand. And you're going to have to understand a lot of that yourself
mhm,
in order to even be able to talk to them in an intelligent way
mhm,
and arrive at a good answer. Um, so that's another piece of advice: be part of a team. Okay, some people are loners, it won't work for them,
mhm,
but find a good team and be part of that team.
mhm,
And and then you can probably contribute a lot more than you could by yourself.
mhm. And any tools, Professor, like taking notes or using memory maps or analogies to keep
Yeah,
yourself motivated and engaged? Sometimes the topic could be dry. So,
yeah.
any tools that you want to share?
Well, I mean, I do take notes. I could show you my stack of notebooks in the corner of my office. It's,
Uh-huh,
very long.
I see.
Uh, to be honest, I don't use them that much, but maybe I think writing it down helps me understand something a little better.
Mhm,
Um, uh, you know, I do make analogies. I understand something by analogy. So the first thing I do when I look at something is I ask myself, what do I know that's kind of like this thing?
mhm,
And once I identify that, how is this thing different than the thing that is a little bit like this thing?
mhm,
And that makes it just much easier to understand.
mhm,
It also helps to think in pictures.
mhm,
Some people do that, some don't. I
mhm,
do. Uh,
mhm.
but I've always wanted to learn techniques like memory maps, and I envy people that can do those kind of things, but I never managed to learn it.
Thanks for sharing, Professor. On the climate effects, we see with El Nino drastic impact on the Pacific tropical countries. Yesterday, there was an article on Guardian about Papua New Guinea severely affected with drought. Can these be forecasted? And how does complex systems modeling apply here in cases like this, where we know something is about to happen? Can we prepare people to handle it?
Yeah. Well, there is some forecasting of El Nino, and meteorologists like Tim Palmer, Michael Gill have developed methods for forecasting and understanding it that
Mhm,
really come out of chaotic dynamics. It's a great example where understanding that there's some low dimensional chaotic dynamic behavior underlying El Nino has been useful in making forecasts. I mean, the forecasts are still not that good,
mhm,
but they're at least a little better than they were without forecasts. And so that's actually a great example where those techniques have been useful in meteorology
mhm.
and climate.
I see. With AI, do you think these will be available to regular audience or only specialists like climatologists? Because I see if they get democratized, I'm assuming your new company is building models like that. So could you tell about your new company, Macrocosm? What is it building?
Yeah. So macrocosm grew out of the other work we were doing in complexity economics. Um, but we wanted to scale things up and reduce them to practice. Meaning, in academia, you have a graduate student, they find some data for some set
Mhm,
of time in the past, they write a paper about it, and they go on and do something else. But
mhm,
if somebody comes to you and says, "What's your forecast for next month?" You, c-
mhm,
you know, well, I have to go get the graduate student, can
mhm.
collect all the data, rerun it, etc.
Yeah.
So the idea is to build models that we can run all the time and scale up by doing models that are much bigger and more complicated than something an individual can do on their own. So
Mhm,
have a large team working on building the model with each member of the team specializing in a role or a portion of the model's
mhm,
behavior. So we're
mhm,
trying to build a model of the global economy,
mhm,
and you could also call it a digital twin of the global economy. And we would really like to represent the whole economy in the model.
mhm,
Every firm with its interactions with other firms, its interactions with consumers, model the populace as a whole,
mhm.
and model economic activity on a fine grained scale that any person could at least see somebody like themselves in the model. And I say that because, we're not interested in confidential information. We'll build a synthetic population. So we won't have Pavan Mirla in the model, but we have somebody who's a little bit like you in the model, close enough to hopefully allow us to give some, decent predictions of what people like you would do and how that will affect the economy as a result. And so that's our goal. We've started by focusing on the energy system.
Mhm,
Within the energy system, we've started by focusing on modeling electricity. So electricity markets,
mhm,
uh, what determines the price of electricity? Uh, how do the agents in electricity markets behave? The
mhm,
agents here would be, say, power stations or um, energy wholesalers that buy electricity and sell it.
mhm,
So how do they behave in the market? What forces do they respond to? What does that do to prices? How does the electricity system evolve in the long term?
mhm,
If we have a given set of rules in place, like incentives for renewables, um, how will the electricity system evolve over time under capitalism? Um, and and we're particularly interested in the question of how can we nudge the world towards green energy faster? How can we get off of our carbon habit and get clean and
mhm.
go green?
I see.
So we think that that's going to happen in the commercial sector, and we need to help the commercial sector understand how to do it profitably,
Mhm,
and
I see.
that better knowledge can really help that.
Assume, I hope that doesn't happen, where we are hit by a pandemic and governments approach you for modeling. So does microcosm does such sort of ad hoc requests modeling? Oh,
Yes, we
mhm,
are doing just that kind of modeling. That's our other big project right now.
mhm,
Um, we this grew out of the model we made for COVID, where I might have mentioned we made very good predictions that we're quite proud of. And we took the concept behind our COVID model
mhm,
and we just generalized it The original model was just applied to the United Kingdom.
Mhm.
We now are applying the model to the entire world,
Mhm.
and um, and modeling disasters like a tsunami in Japan or an earthquake in Japan.
Mhm.
I mentioned Japan because we have a client there that we've been building models for specifically.
Mhm.
But when the Straits of Hormuz got closed,
Mhm.
we issued a report predicting what we thought the economic consequences would be, conditional on how long the strait remains closed.
Mhm.
And so we did that about 7 weeks ago.
Mhm.
And so we've been tracking to see whether our predictions are right since then. And they look
Mhm.
pretty good. And most the times where they're not good is more because we weren't able to get our reading of the data was wrong. For example,
Mhm.
we predicted things would be pretty bad for India. They aren't as
Mhm.
bad as we predicted. That's because India's oil reserves were bigger than we thought. The
Mhm.
public oil reserves were only a week and a half, but there were a lot of private oil reserves,
Mhm.
and we didn't realize that.
Mhm.
So those are the two problems we're starting with, but our long-term goal is to really model the entire global economy and the financial system, and really try and guide the world towards a more sustainable yet prosperous economy.
Professor, thank you very much for making time to talk to us today. Thank you very much, Professor.
It's my pleasure.